Symmetry seems to be absolutely fascinating to the human mind. We like to look at the symmetrical things in nature, such as the perfectly symmetrical spheres like the planets and the sun, or symmetrical crystals like the snowflakes, or flowers which are nearly symmetrical. However, it is not the symmetry of the object in the nature that I want to discuss here. It is rather the symmetry of the physics laws themselves. Physics laws themselves, right? Richard P. Feynman. The Character of Physical Law, Chapter 4. I want to shift gears here a little bit for the next couple of lectures and talk not about the constituents, the particle and quarks and electrons that make up the world, but to talk about a little bit more abstractly about the rules, the laws of physics. The tools that physicists use to try to understand how the world works. Both are important for particle physicists to know what we are made of and also how those things fit together in a theoretical framework to understand the workings of the microscopic world. One of the most powerful tools that particle physicists use nowadays is a principle of symmetry. It's very useful. It has both practical consequences and aesthetic consequences. And I want to spend this entire lecture just talking about what physicists mean by symmetry, and why and how it's useful if you want to understand the world of particle physics. In fact, it's much more general than just particle physics. Any kind of the physicist or even a biologist or a chemist or any kind of scientist nowadays is going to know about symmetry and care about symmetry. As you'll see, it's a very powerful guiding principle, right? Physicists often use the words in the way that are unfamiliar. When I talk about force, I mean something very definite. It's a push or pull. In the English language, the word force can mean, I don't know, forces of nature, the great force of an army, or may the force be with you. In English, these words have lots of meanings, and in physics, we always make a definition and it's usually mathematically based. The word symmetry is pretty much what you think it is. It's just a little bit more general. To a physicist, symmetry means when you take an object or a system or anything and you look at it from the different perspective. If it looks the same from the two different perspectives, then we say it's a symmetrical. So think of a snowflake. A snowflake has a six-fold symmetry, and that means that if you rotate it by 1/6 of the turn, it looks exactly the same as when you started. Or you could tilt your head by a 1/6 of the turn, it would look the same. So that's a symmetrical object, because when viewed from the different perspective, it's uncharged. Now you can talk about the symmetries of objects. But you can also talk about more abstract symmetries. You can talk about symmetry of mathematical theory, and you don't mean that if you tip your head, the symbols look the same. What you mean is that if you make some change in the perspective, some change in how you look at the theory, the answers comes out the same. We'll talk about some concrete example of the symmetry in the theories coming up very shortly, right? The mathematics of symmetry is called group theory, and once upon a time this mathematics was very obscure. It became more important for physicists to learn about group theory in the early 1900s when quantum mechanics was developing. And group theory is really just a mathematical formalism that describes what different kinds of the symmetries there are in the world. Turns out there is a different sorts. There is a geometrical symmetries and more abstract kinds. And nowadays, it's an essential ingredient in the toolbox of pretty much any working scientist. We are not going to learn group theory in this course, but I want to talk about the basic ideas, the underlying principles behind the story. snowflake is a nice concrete example because you can visualize it. Geometric symmetry is pretty easy to visualize. Another symmetry is left-right symmetry on my body. This side and that side look pretty much the same. We'll talk a little bit more about imperfections or breaking of symmetries in the next lecture when we start looking in fine details. But for today, I just want to focus on the perfect symmetries. So I want to make a kind of a first metaphor, or I don't know, some sort of the concrete example of a symmetry which is not a geometrical in character. And I'm stretching a little bit here, but I want you to imagine that you are in the foreign country on a holiday, and you see a bunch of kids out on the field, and they are playing. It's obvious that there is some sort of the game going on. They are in the confined area, and you are watching, and you notice that some of the kids have been short, and some of the kids have red shirts, right? Sorry. So you are watching and you notice that some of the kids have green shirts and some of the kids have red shirts, and otherwise you don't know what's going on down there. There is just a whole bunch of screaming and fun activities. There are various ways you could try to figure out what's going on. What is the nature of this game? Well, if you can't speak the language, you can't ask somebody what the rules are. Now, supposing you notice there is a pile of extra shirt off on the side, and so, you sort of do the foreign language pantomime thing, and you get all the kinds with red shirts to put on green. So, now everybody wearing green shirts, okay? Right. This is an experiment that you just did to learn about the symmetry of the situation. So now you let them go. Watch what happens. There is a various possibilities. One is that they combine to play just the way they were before. They are still running around and screaming, and now you've heard that there is a very deep symmetry in this game. That color is completely irrelevant. So my definition of the symmetry was, you change something, but then the result looks the same. Here we changed the color of half of the players, and the end result is the same. This is a complete symmetry of color in this game, and what have you learned? Well, it can't be a competitive game unless the kids know each other so well that it doesn't matter what the color of the shirt is. But one possible conclusion is it's one of those new fangled cooperative games where it doesn't really matter. There is not teams. The kids just wear whatever shirts they feel like, and it was just a coincidence when you first looked that it was a 50-50 and they are playing some game that's not competitive. So you learn something, and of course, it's not going to teach you everything about the game. Symmetry is just one tool among many. There is another possibility, which is that everybody is green, and then they just all kind of stand around. They don't know what to do. Then it's more likely that the game was competitive, and you need to have two teams. And now the kids are confused because they don't know who's on what teams. So again, by looking either at symmetry or lack of symmetry, you can learn something about the rules of the game. Now, you might continue to do further symmetry experiments. For example, instead of just making everybody green, you could swap so all the reds become green and all the greens become red. And again, there is a various possible outcomes. It's possible that the game will proceed just as before. So now you would say there is a symmetry. It's not the deepest possible symmetry, but there is a nice symmetry which is under color interchange. the rules of the game are unaffected, so apparently color doesn't matter. Most games are like that. In soccer team, it doesn't matter if your team is red or green. All that matter is that you have two different colors, and so again, you've learned something about the nature of the game. Now you could imagine a situation where you flipped the colors and the game changes in some way. It might be that blue-eyed kids have to wear a red shirt, and if they don't, they are all confused, because that's the way it's always been. That's what maybe even the rule says. It would be a slightly unusual situation, but you'd learn something. This is a little bit of a stretched example of the symmetry, but I wanted to come up with something that I wasn't just geometrical, where you rotate an object on or flip it, and it looks the same. Right. And in fact, this analogy is a good one for the strong nuclear force, where you have protons and neutrons that combine together to form a nucleus. So we'll take one step back up from the quarks for a moment. In the 1930s, people were busily trying to understand the nature of that force. How does a proton attract another proton or another neutron? How do neutrons attract one another? That was the nuclear physics, and people were very interested. It is the essence of the strong force, and it was, in a certain sense, like my little game analogy. What you discovered was a color was completely irrelevant, or in this case, whether you're a proton or a neutron, which team you're on, didn't matter. Proton attracts protons, protons attracts neutrons, neutrons attract neutrons. There is no change in the rule of the game when you change the nature of the particle from the proton to neutron. So there is a proton-neutron symmetry of the strong force, which we are observing, and that taught us something very important about the nature of the protons and the nature of the strong force. Later, we come to understand that more deeply as a connection that says up quarks and down quarks are almost the same object, and the strong force doesn't care about whether you are an up quark or down quark. It really only cares about the strong color charges inside, which is something totally different than whether you are a proton or whether you are a neutron. Now, it's also true that what I said is only approximate. There is a slight difference between the proton-proton and proton-neutron, and that sunlight breaking of the symmetry is also going to teach us something. That will be the subject of the next lecture, where we look at what violations or breaking of the symmetry teaches us, right? But for right now, I just want to continue to focus on what symmetry teaches us. So in this case, we've learned something about the nature of the nuclear force. It has simplified our worldview. If you are a nuclear physicist and you are trying to describe a nucleus mathematically, you don't have to label each particle proton or neutron. At least at some crude level you don't have to, because it doesn't matter. So you've simplified your job, you've simplified the mathematics, you have reduced the number of degrees of freedom that you have to keep track of. And that's very useful and powerful goal in any science to simplify the explanation of the phenomena. So that's one value of symmetry. Think back to that snowflake example, which is a geometrical. If you rotate a snowflake by 60 degrees, it looks the same as it did before, and that teaches you something about individual crystals that are building up the snowflake. I'm not saying that all snowflakes look the same, but they have this general property of symmetry which is always common, and the fact that essentially all snowflakes have that symmetry teaches us something about the shape of the crystal inside. Even before we were capable of looking with the electron microscope or the laws of the quantum mechanics to figure out exactly what an ice crystal looks like, we already knew something about it just by looking at this microscopic object that had symmetry. So sometimes, rather than saying it simplifies, you can say that a symmetry teaches you about what's going on inside. Another powerful use of symmetry. There is more. Symmetry has many functions and values in the world. Of course, it's also nice to look at something that's symmetrical, something about our nature as human beings. When I look at a snowflake, it just looks beautiful to me, and in part, it's because of that symmetry. It seems like it makes the object feel simpler to me, and so when we are looking for theories, I think there is just kind of the natural human desire to look for symmetrical theories in some way. There was a mathematical theorem which was published in the 1915 by a mathematician named Noether, and it's a quite famous mathematical theorem. I usually don't want to teach math in this course, but in this one, without going into the details, again, we can talk about essence, and it's had a lot of implication in particle physics. Emmy Noether was raised and lived most of her life in Germany in the late 1800s, early 1900s, and it was a very difficult time for women to be a mathematician. The German institutions were incredibly sexist. She was, in principle, not allowed to take college courses or get her PhD, and she kinda did it by going to professors who were a little bit more liberated than the institution themselves, and they allowed her to sit on the classes. So she basically worked her way through to her PhD in mathematics against the sort of desire of some of the higher ups. And even after that, when she had her PhD, she took a position at the university, and it was essentially an assistant professor position. She was teaching, she was doing research, and she didn't get paid. Really? It took her many years before she could finally convince people to pay her for this job. Crazy. But despite all of this adversity, she was a fantastic mathematician. She was a mentor to many young students, unfortunately mostly men, who later became great mathematicians as well. And this theorem in the 1915 was a mathematical statement that connected symmetry to something a little bit more concrete, which are conservation laws. Wow! Now, the details are a little fancy, and in fact the theorem is probably a little bit less general than what I'm going to imply here. You really need some fairly special assumptions and special cases for this theorem to hold, but the general statement is this. Noether's theorem argues, if you have a very specific symmetry, then you are guaranteed to have a conservation law associated with your system. Really? Wow! So cool. Again. Let me repeat it again. Yes. If you have a very specific symmetry, then you are guaranteed to have a conservation law associated with your system. Let me remind you what the conservation law means. Conservation law means that you start with some quantity, and then all sort of the complicated stuff can happen, and then in the end you've still got the same amount of that original quantity. For example, you started out with some energy. It might change forms E equal mc square. You might create matter and antimatter. It might re-annihilate. But in the end, you always will have the same total energy as what you started with. Or electric charge. That's also conserved if you start off with the interaction of the particles. It doesn't matter what the nature of that interaction is. Electrical, magnetic, strong, weak. it's always true that whether the charges you begin with, it could be a big blob and big mess and lots of confusion, and then when the dust settles, whatever comes out has the same charge as what you started with. Wow. Conservation laws are wonderful for physicists. We teach them to freshman students and we keep reminding them over the years as they go on. There are more and more sophisticated and complex kinds of the conservation laws. They make understanding a complicated system very easy because it eliminates from the consideration an enormous amount of physically impossible outcomes. When you've got the particles smashing together, you might throw up your hands in dismay and say, anything could happen, it's a quantum mechanics probabilities, right? Anything could happen, but many things can't happen. You can't create charge out of the nowhere, so physicists love conservation laws and it's practical. You know, police go to the accident scene and they use conservation of momentum, looking at the tire tracks to conclude whether the original driver was speeding, and so they can decide whether to give somebody a ticket by using a conservation law. This is, real world stuff.